2.4, linear functions. So we've talked about functions in general. Now we're going to talk about linear functions. Linear functions are functions that can be defined in the form f of x is equal to ax plus b, where a and b are both real numbers and a is not equal to 0. I'm going to put that a not equal to 0 because that's very important, because if we have a equal to 0, then it doesn't matter what x is, and we end up with f of x is equal to b, which is not a function really. It's a horizontal line, but it's not a function of x. I shouldn't say it's not a function. It's not a function of x, because x will not have any effect on the output. So linear functions, f of x is equal to ax plus b, where a and b are real numbers, and a is not equal to 0. Now when you have these functions, then we can actually, since that's a line, lines will have what we call intercepts. Intercepts are where the line crosses the x-axis and the y-axis. If we take f of 0, x, which is basically saying let x equal to 0, then we will get the y-intercept. And that's just an abbreviation for intercept, y-int, y-intercept. So we set x equal to 0, then we will get the y-intercept, basically, where it crosses the y-axis. If we set y equal to 0, so if we say f of x is equal to 0, then we will find the x-intercept. So if you want to find the intercept, set y equal to 0, set x equal to 0, solve, and you find out the other value to determine what the intercepts are. Once you have the intercepts, you can draw the line, because a line is straight, so all you need are 2 points to be able to draw a line. Well, what happens if the intercepts happen to be the origin? Well, if the intercepts happen to be the origin, then that gives you 1 point. You're going to need a second point. Choose some value of x and plug it in, or choose some value of y, plug it in, and find a second point on the line. So let's try this. F of x is equal to 4x minus 3. So we want to find the intercepts, the y-intercept and the x-intercept. Now you'd think we would say x-intercept and y-intercept, but we generally say y-intercept and x-intercept because y is usually what we find first, because y is found by plugging 0 in for x. And then we go the opposite direction to find the x-intercept by plugging 0 in for y. So it's kind of that order we go in, because the y-intercepts come from setting your input to 0. The x-intercept come from setting your output to 0. So if we have this and we go f of 0 is equal to 4 times 0 minus 3. 4 times 0 is 0, so negative 3. So I would prefer to see the y-intercept given as an ordered pair, as a point. So I would say that's 0, negative 3. Can you technically say that it's y equal to negative 3? Well, yes, because intercept by definition says that's where it's crossing it, therefore x must be 0. But I much prefer to see the point. And the reason I prefer that is because that eliminates any confusion that I or you may have about what is going on there. The point 0, negative 3 is where it crosses the x-axis. So that's something we can plot, that's a point. Now if we want to get the x-intercept, we're going to say 4x minus 3 is equal to 0. So we're going to set the function equal to 0, or y equal to 0. So now we're going to solve for that x. So add 3 to both sides, 4x is equal to 3, divide both sides by 4, x is equal to 3/4. So now I would say that the x-intercept, and again I like to see it as a point, an ordered pair, is 3/4, 0. So we have our y-intercept and our x-intercept, which now allows us to graph this line. Before, remember, always number these. Yes, I will keep harping on that the whole time. And yes, I do take off points if you don't number your axes. Some of you may have seen that already. So we have this, that's my grid. Tried to make it somewhat reasonable so the line would come out close to correct. So I'm going to plot my 2 points. I've got my y-intercept, which is 0, -3, 0, -3. And then I've got my x-intercept, 3/4, 0. 3/4, 0. So now we have that. I take my straight edge and use that to make sure that I get a perfectly straight line. Now don't pretend like you didn't see me use a straight edge. Okay? So I've got my line, and there it is. I put it through those 2 points, and all is good. Now I will point something out here. When we had this function, f of x is equal to 4x minus 3, or we had f of x is equal to ax plus b, that's really a form that you've seen before. That's the slope-intercept form. You've seen it as y equals mx plus b. And as a function, we say it's f of x is equal to ax plus b, where a is the slope of the line, and b is the y-intercept. Notice in this here that when we solved for f of 0, we got -3 as our y-intercept, our y value, and that was b, that was the y-intercept. So that's why that's called the slope-intercept form. This gives you the slope of the line. This gives you where it crosses the y-axis, what happens when x is equal to 0. So we don't have to necessarily plug in values for that. If we've got it in slope-intercept form and we want to find the y-intercept, you just look for the constant term. And that's it. That's going to give you your intercept. Now technically we could plot a line just by finding any 2 points on the line. We don't need to necessarily find the intercepts, but quite often we'll be asked to find the intercepts. And really the intercepts are the easiest points to find, because remember, the easiest numbers to work with in mathematics are 0 and 1. And especially in something like a linear function like that, working with 0 is awesome, because you plug in 0 for x, it wipes out the variable term, and you're just left with the constant. Remember, 0 multiplied by things wipes them out, it just turns them into 0, which is very nice to work with. So that's why we tend to like our intercepts. They're very easy to plot because you just need to find that one value, and you just have to plug in 0 for x, which is usually a much easier number to work with than anything else. So that's very good. What we also want to talk about is the standard form. So we have the slope-intercept form. F of x is equal to ax plus b. I just wanted to note that for you, right? The slope-intercept form. We also have the standard form. Standard form is, and I just want to make sure that I'm using capital letters for this, so ax plus by is equal to, oops, that should be a capital C. So this is called the standard form. Standard form, ax plus by is equal to c. And this is a function in two variables, right, x and y. We could have a linear function in three variables, x, y, and z. And that would be ax plus by plus cz is equal to d in standard form. This is called the standard form. In standard form, we tend to like to have integers for these constants a, b, and c. We like to have integers for them. Now that's not to say that you're never going to see them with decimals there, but we definitely don't like to see fractions, and in general we like to see them as constants. So once we get it into this form, we want to make sure that we're not looking at a fraction or a decimal. We'd like to see it as a constant. That's all I'm saying, right? So this is standard form. Now standard form, a little bit harder to look at initially and to read things. It's not slope-intercept form. I can't just pull the slope and the intercept out of this. But if you notice, plugging in 0 is really easy. Right? If I plug in 0 for x, then by is equal to c. So our y-intercept is going to be c over b. And if we plug in 0 for y, then we get ax is equal to c. So our x-intercept will be c over a. So it can be really easy to pull those intercepts out of it, which makes it easy to plot. So if I have 3x minus 2y is equal to 6, then I can pull my intercepts. Well, we get the y-intercept by making x equal to 0. So our y-intercept, if x is equal to 0, then we have negative 2y is equal to 6. Negative 2y is equal to 6. Or y is equal to 6 over negative 2, which is negative 3. So 0, negative 3. If I want my x-intercept, then set y equal to 0, and I get 3x is equal to 6, or x is equal to 2. So 2, 0. Quick and easy to find, and once we have those two, we can plot it. I'm not going to number my axes in this just because I'm doing the quick demonstration, but you have 2, 0, and 0, negative 3. I said 0, negative 3. And we're able to plot our line. Always number your axes, and don't drop your eraser on the floor. So that's the standard form. Now, we can convert back and forth between the standard form and the slope-intercept form, which I'm going to come here and I'm going to modify this. Like, we know this is a function, right? But I'm going to just put this as y is equal to ax plus b. So now we have both of these in terms of two variables, x and y. If we have an equation for a line in the form y equals ax plus b, or the slope-intercept form, we can move the variables around, move everything around, the terms and such, and we can put it into standard form. If we have it in standard form, we can move it into slope-intercept form. So let's take an example of that. If I have y is equal to 3x minus 1, that's in slope-intercept form, and I want to put that into standard form, then all I'm going to do is get x and y on the same side. I generally prefer to have the leading coefficient be positive, so I'm going to move y over to this side. So I'm going to subtract y from both sides, making this 0 is equal to 3x minus y minus 1. But in standard form, we need ax plus by equal to c, so I'm going to move the constant over to the other side. And you're not going to like this, but what I'm going to do is I'm going to at the same time flip it. So I'm just going to call it 3x minus y is equal to, if I add 1 to both sides, is equal to 1. So a is 3, b is negative 1, c is 1. And that is now in standard form. Well, what if I start with a linear function in standard form? 5x minus 2y is equal to 9. And I want to put it into slope-intercept form. That means I'm just solving for y. So I want to get y by itself. So subtract 5x from both sides. Negative 2y is equal to 9 minus 5x. Divide both sides by negative 2. Y is equal to 9 minus 5x over negative 2. Now, obviously, that's not in slope-intercept form yet. Keyword being yet. Now we've got this 9 minus 5x divided by 2. Well, I can split that up into two fractions, can I? Or two rational expressions. 9 over negative 2 and negative 5x over negative 2. So I can say y is equal to 9 over negative 2 plus negative 5x over negative 2. Yes, I could have made that a minus. I just chose to take them in separate pieces and treat that as negative 5x. Now, last thing to do is simplify if possible and just swap the position of these to get it into the ax plus b form as opposed to b plus ax. So y is equal to negative 9 halves. Negative 5 over negative 2, the negatives cancel out. So, oops, remember what I said, I want to swap the position at the same time, so let's do this one first. Negative 5 over negative 2 cancels out, so we have 5 halves x, and then 9 over negative 2 gives you minus 9 halves. So now we're in slope-intercept form. What's the y-intercept? Negative 9 halves. So 0, negative 9 halves, or 0, 4.5, right? So this is in slope-intercept form. Remember, it's standard form that you need to have them, and you want to have them as integers. It's okay to have fractions and or decimals in slope-intercept form if you can keep it as a fraction as opposed to rounding a decimal, then keep it as a fraction. This, of course, 5 halves, 2.5. 9 halves, 4.5. So we could do this as 2.5x minus 4.5, and that's still exact. But if you have something that's going to round, it's better to leave it as an exact fraction than to turn it into an estimated decimal. Okay. Let's talk about this slope thing. I'm going to leave these up here because there's going to be one more form that I want to put up here. Let's talk about this slope thing. We've mentioned it, but we haven't done anything with it. Slope is just a measure of rise over run change in y over change in x. So slope, which in this case we're using a, but usually we say slope is m. That's the variable that we use for slope. And that is equal to the change in y over the change in x. That triangle means delta. Delta is the symbol for change in mathematics and science. So, and engineering, but engineering is mathematics and science. So delta just means change. So the change in x over the change in y. The rise, how much does it move up or down, over the run, how much does it move side to side? Or, sorry, not x, y2 minus y1 over x2 minus x1, where 2 points are x1, y1 and x2, y2. So change in y over change in x, the rise of the run, or y2 minus y1 over x2 minus x1. Now I will tell you, when you're finding the slope, it doesn't matter which point you call x1, y1 and which point you call x2, y2, as long as you are consistent in doing so. So don't use this point to give you x1 and this point and call it y1, because that'll throw off your slope. So let's use this. I'm going to get that out of the way, and I'm just going to put it up here. M is equal to y2 minus y1 over x2 minus x1, just so we have it there as a reminder. So if I have 2 points, -2, 3, and 5, 6, and I want to find the slope, the slope is equal to the change in y over change in x. So I'm going to treat this as x1, y1, and this is x2, y2 initially. So I'm going to do that just to remember that they relate correctly. So we want to take change in y, 6 minus 3, over change in x, 5 minus -2. 6 minus 3 is 3, 5 minus -2 is the same as 5 plus 2, so 7. So the slope is 3/7. Now I'm going to change this up a little bit, and only a little bit. I'm going to call this point x2, y2, and this one x1, y1. Not y1. So now my slope is equal to 3 minus 6 over -2 minus 5. 3 minus 6 is -3. -2 minus 5 is -7. Negative divided by a negative is positive, gives you 3/7. So notice it doesn't matter which point you call the first point, which point you call the second point. The slope, as long as you don't do anything foolish, will end up being the same. And by foolish, I mean it's very easy for us to oops and start here and go 6 minus 3, and then go -2 minus 5, where you swapped the direction of your subtraction. Instead of subtracting this from this, and then this from this, you went this from this, and this from that. So that's where we make a mistake, and our slope ends up wrong, which is not good. What does it do to it? Well, it'll actually, if you make that mistake, it'll just negate your slope. Instead of coming up with 3/7, we would come up with -3/7. So I guess I should say, well, what does that tell you? If you have a positive slope, if m is greater than 0, then it is increasing, meaning as x increases, y increases. If m is less than 0, your slope is negative, then it is decreasing. So as x increases, y decreases. If m is equal to 0, it's constant. So if m is equal to 0. There's one other thing that can happen when you're dealing with lines, and I say when you're dealing with lines because it is not a function. You can have an increasing line, that's a function, a linear function. You can have a decreasing line, that's a linear function. You can have a constant line, that's still a linear function. But if your slope is, I shouldn't say infinite, if it's undefined, then you have a vertical line. X remains the same and y increases an infinite amount. Remember, it's change in y over change in x. So if x stays the same, you're dividing by 0 and therefore it's undefined. So if you have a slope that's undefined, you have a vertical line. If you have a slope that is equal to 0, you have a constant function or a horizontal line. So a horizontal line. So recognizing slope and what it tells us. Well, now that we know about slope, there's actually something else that's really cool that we can do. Using something similar to slope. Well, actually, before we do that, let me just get into this last form here, since those are sitting up nicely. I just wanted to get into the fun stuff, but the other way that we can do this is there's another form, y minus y1 is equal to m times x minus x1. And this is called the point slope form. Point slope, if we have the slope of the line and we have a point on the line, x1, y1, then this is an equation for that line. So if I have a line with a slope of -2 and a point on the line -1, 5, then I can come up with an equation for that line, because I'm just going to go y minus 5 is equal to the slope, -2 times x minus -1. Now remember, I always do this putting the parentheses in there and putting in the negative as opposed to changing this immediately, because really x minus -1 is x plus 1. But the form is x minus x1. So I want to make sure that I don't make a mistake of accidentally saying x minus 1, because that would not be this point, that would be the point 1,5. So I do that. So now this is technically in point slope form. We have the slope of the line and we have a point on the line. Now this can be turned into either slope-intercept form or standard form. So let's do that. Well, the first thing I'm going to do is I'm going to distribute this through. So I'm going to cancel that and distribute through that -2. So I'm going to say y minus 5 is equal to, well, I'm going to do -2 x plus 1. I'm going to do that first and then I'll distribute it through just so it doesn't get confusing. Y minus 5 is equal to -2x minus 2. Now we can see at this point that it's actually pretty easy to go from here to either y equals ax plus b, or ax plus bx plus by is equal to c. So I'm going to go for slope-intercept form at this point, just because, boy, we're right there. So y is equal to, I'm just going to add 5 to both sides, negative 2x plus 3. Negative 2 plus 5 gives you positive 3. So y is equal to negative 2x plus 3. And we can see that the slope is the same as what we started with in the slope that we had for that line. So that's good. What I can also do is I can go into the ax plus by equal to c form, and I can even do that right from here, add 2x to both sides, and I got 2x plus y is equal to 3, and now I'm in standard form. So we have point slope form, slope intercept form, standard form. And we can bounce back and forth between all three of those. And we could take any of those forms, so I just want to circle them as these are the forms that we've dealt with. I can take any of those forms and plug in x values and get y values. So they're no different, and they will all plot out to be the exact same thing. So those are our three different equations that we used. Slope-intercept form, standard form, point-slope form. Practice with them. Make sure that you can convert from one form to the others, and vice versa. So start with something in slope-intercept form, which you can create your own just by saying y equal to, choose a constant, x plus, choose some other constant. And then convert that to standard form, and convert it to, well, you generally don't start at slope-intercept form or standard form and convert to point-slope form. So I won't say convert to those, but start it and do the slope-intercept form, convert it to standard form. Choose three numbers at random and plug them in for a, b, and c in the standard form. Now solve for y and get into the slope-intercept form. Again, you don't usually start in standard form and then go to point-slope form. The other thing is, point-slope form, choose a number for your slope and choose a random point, x, y. Or x1, y1 to be clear with that. And plug it in there. Now convert that to standard form, convert it to slope-intercept form. So it's very easy to create your own to play with. And then to verify them, just choose a value for x or y. If I want to make sure these are all the same, let's just plug in x equal to 1. If x is equal to 1, then I have 1 plus 1 is 2. 2 times 2 is negative 4. So I have y minus 5 is equal to negative 4. And then add 5 to both sides. Y is equal to 1. So when x is 1, y is 1. Well, if that's true, that should work in this one too. If I plug in 1 for x, I get negative 2 plus 3. Negative 2 plus 3 is 1. If x is equal to 1, y is equal to 1. If I plug in 1 for x here, 2 times 1 is x. So, 2 times 1 is 2. 2 plus y equal to 3. 2 plus y equal to 3. Subtract 2 from both sides. Y equal to 1. So there we are again. And we're good to go with that. So you can verify, did they work out just by plugging a value in for x and see if you get y the same for each of your forms. So really handy to be able to do that. Okay, so what we also want to deal with is rate of change. Rate of change is basically saying that not all functions are linear, but we can look at them kind of in a linear way and get their slope between 2 points. So basically, we call it average rate of change. AVG, average rate of change is just the same formula, y2 minus y1 over x2 minus x1. So we got our average rate of change. So if I have a function and I have 2 points on that function, then I can find the average rate of change, or if I even know, if I want to find 2 points on the function, I can do this. So let's say I have y is equal to 2x squared minus 7. And I want to find the average rate of change from x equal to 3 and x equal to negative 1. So I want to find the average rate of change. Well, what can I do? Well, to find the points here, I've got x, so I'm just going to say y is equal to 2 times 3 squared minus 7 is equal to 3 squared is 9, 9 times 2 is 18, 18 minus 7 is 11. And then I can do the same thing with x equal to negative 1, so y is equal to 2 times negative 1 squared minus 7. Negative 1 squared is 1, 1 times 2 is 2, 2 minus 7 is negative 5. So now I have 2 points. I have 3, 11, and I have negative 1, negative 5. So I have 2 points on this curve. So I want to plug that in now and see what I get for my average rate of change. And that's just like finding slope, and I'm just going to abbreviate it ARC, average rate of change. So I'm going to treat this as x2, y2, and x1, y1, just because this one's above that one. Just my choice. So change in y, negative 5 minus 11. Change in x, negative 1 minus 3. Negative 5 minus 11 is negative 16. Negative 1 minus 3 is negative 4. Negative 16 divided by negative 4 is positive 4. So our average rate of change for this function from x equal to 3 to x equal to negative 1 is 4. So average rate of change. It's just finding slope, but we're finding slope by using 2 points on something that's not necessarily straight. In fact, this is a parabola. It's a nice curve. But we can take any 2 points on that curve and find the slope between those 2 points, which we call the average rate of change. So the last thing I want to go into is I just want to show a quick thing, and I know I'm off screen, but I will be right back on in a moment. Okay? I want to talk about cost, revenue, and profit functions. A cost function many times is a linear function. C of x is equal to ax plus b, where b is a fixed cost and a is a variable cost, meaning that for each unit x that we produce, there's a certain cost associated with that, and then there's just the thing you have to pay for no matter what. If you've got to pay the rent whether you make one product or whether you make 1,000,000 products. You still have to pay for the rent. So that's a fixed cost. Whereas variable cost would be the materials that you put into the product. If you're only making one, you only have to buy enough material to make one. Whereas if you're making 1,000,000, you have to buy enough material to make 1,000,000. So this would be the cost function. The revenue function, R of X, the revenue, that's basically the money that comes in, is just a function of Px, the price per unit multiplied by the number of units. Also a linear function. You don't produce any units, you don't get any revenue. You produce 1,000,000 units, you get 1,000,000 times the price that you charge per unit. So another linear function. And then there's the profit function, and that's a lowercase p because that's the price. The profit function, capital P of X, is the revenue minus the cost. So it's the revenue function minus the cost function. And that gives you your profit. If you produce X units, what's your profit going to be? And it depends on what's your cost per unit and what is your price per unit, your revenue with that. So let's try an example of this and see. So I'm going to create some functions here. I'm going to get these out of the way because we're just going to build them together. So let's say, and we're going to keep things relatively simple, we're not going to get into these multi-million-dollar things, but let's assume that you have to pay $500 a month rent on the facility that you're using, and it costs you $7 for each product you produce. So you take $7 worth of materials to go into that. So you're paying $500 for your space, and you're paying $7 per unit that you produce to cover costs, labor, whatever the case may be. So now we have a cost function. If I produce 10 items, it's going to cost me 7 times 10 plus 500. So 7 times 10 is 70 plus 500. It's going to cost me $570 to produce those 10 items. So let me just show that there. C of 10 items is equal to 7 times 10 plus 500 is equal to $570. That's what it cost me to produce 10 items. Now you may notice with this, because we have this large fixed cost, that our cost per unit actually goes down the more units we produce. Not our variable cost, that stays the same, but here, 10 units cost us $570. That means each unit cost us $57 to produce because of this fixed cost. Whereas, I'm going to get this Rx, R of X, and P of X out of the way for the moment. If we produce 100 units, then we have 7 times 100 plus 500. 7 times 100 is 700, plus 500 is 1,200. And now we see that to produce 100 units, it cost us $1,200 or $12 per unit. Have you ever heard of economies of scale? This is a great example of that. By producing more, I'm able to reduce my cost per unit. 100 units for $1,200, I just produced them for $12 each. When I was only producing 10 units, it cost me $57 each. So look at that huge cut in costs. So if I can produce more, I can produce it for less. So we have that. Now let's go for our revenue function. So we have this product that we're producing, and we determine that we're going to sell it for $30. So 30x, the price times x, the numbers of units produced. So if I produce 10 units, R of 10, I have 30 times 10, or I just made $300. If I produce 100 units, I have 30 times 100, or I just made $3,000, or sold them for a total of $3,000. So there's our revenue function. The more we sell, the more money that we bring in. On top of that, we have the profit function. Because realize that that revenue that we bring in does not represent what we actually make. Revenue is just what gets paid into you. It doesn't account for how much you paid out to get there. If you spend $100 to make $200, so basically you put out $100 and in return you get $200 back, you didn't make $200. You really only made $100 because it cost you $100 to get that $200. It's like if you buy a car for $1,000 and turn around and sell it for $2,000, you didn't just make $2,000. You made $1,000. You doubled your money. You got $1,000, not $2,000. So the profit function is just the revenue function, in this case 30x, minus the cost function. How much did it cost you to make it? 7x plus 500. Put that in parentheses because we're subtracting the whole thing. So we can say that our profit function is 300 minus 7x, 30x minus 7x, which is 23x, minus 500. Distribute that through negative 7x minus 500. So it's 23x minus 500. So if I want to know how much profit am I going to make off of, well, we were dealing with 10 units and 100 units, right? So if I want to find out what my profit is for 10 units, then I'm going to plug in 10, so 23 times 10 minus 500. 23 times 10 is 230. 230 minus 500 gives you negative 270. So by producing 10 of them, I just lost $270. Not a good business plan. But if I produce 100 of them, then 23 times 100 minus 500. So that's 2,300 minus 500 gives me 1,800. So by producing 100, I just made a profit of $1,800. And that's the idea of cost, revenue, and profit functions. And you may even go to the point of saying, well, what's my break-even point? At what point does it become worthwhile to even do this business? Obviously, producing 10 of them was not worthwhile. Producing 100, it was. I made money off of that. So how do I find my break-even point? Well, your break-even point is where your cost and your revenue are equal, or the difference between them is 0. Oh, I got rid of that other thing. Let me put that back in here. So there's 23x minus 500. I'm just going to put that there as P of x. That's my profit. So if I want to find out what's my break-even point, how many of these items do I need to make to break even or to start making a profit, I'm just going to set my profit equal to 0. 23x minus 500. I want to get x by itself, so we're going to add 500 to both sides. 500 is equal to 23x. I'm going to divide both sides by 23. X is equal to 500 divided by 23. I'm going to reach over and grab my calculator because I don't want to do that in my head. 500 divided by 23 gives me 21.739. So my break-even point is at 21.739 units. So I have to make at least that many to start making a profit. So my break-even point is 22 units. And that finishes up section 2.4, linear functions.